Welcome back to chapter 35 from Physics for Scientists and Engineers. So last video I went through these sections very quickly. I kind of spent a bit more time on 35.1, point 2, point 3, and then point 4, point 5, point 6, point 7, point 8. We went through those like very quickly and I kind of didn't have any idea. So let's say that you did a quick read through of the chapter or the notes or whatever, and then you went to class, checked out the lecture, and it kind of spoke about some of these things. Now it is after the lecture and you have some free time and you would like to take a look at the book a little deeper. Me personally, as I read through this, there's some parts that stuck out to me a little more. So for example, the ray approximation in geometric optics, 35.3, and the wave under reflection, 35.4, I think those parts are fairly solid for me. And there's this thing that happens to me that may happen to some of y'all where you keep reading the same thing over and over and it just gets really boring. So for example, in this section, I've opened this chapter 35 so many times and I'm just tired of the beginning of it. So feel free to read other parts. You don't have to just read linearly from start to finish and absorb all the information, one section at a time. Sometimes what I do is actually start from the end and go backwards. So 35.8, total internal reflection, and then go back to dispersion, Huygens principle, the wave under refraction, and meet kind of in the middle where my knowledge gets a bit stronger. So we might do something like that today. We're going to do it a little bit differently. I'm going to start from section 35.6, Huygens principle, and I'll show you why. So let's say I open this book here, this chapter, and I'm just like looking through. It gives a little bit of an introductory paragraph. Take a look at my previous video to see me speed run through this in 7 minutes. We got the nature of light, section 35.1. Measurements of the speed of light. We have two measurement methods here, Romer's method and Fizeau's method. I will have a video on Fizeau's method soon, taking a look at this example here. Then we have 35.3, the ray approximation. Very short section. You can see it's 3 paragraphs here with a picture. So you can take a look through this. There's for sure some information we missed out on in the 7-minute run through. So if you're interested and you're curious about the ray approximation, some more parts about it, I recommend reading through this. It's going to be, interesting. Basically, study based on your interest. That's the way you get least bored. If you just force yourself to digest this stuff, it's going to get really boring really quick. So that's what I'm going to do today for me. Each person thinks differently. They have their own interests. So when I see this ray approximation, I'm just like, I don't really want to read this too much. Same thing with wave under reflection, 35.4. I don't really feel like reading through this right now. I have a general grasp of what it's saying. Same thing with this problem. I don't want to deal with it right now. I might look at it a bit later. And same thing with this, the wave under refraction. I do not want to look at this for now. I have maybe a general grasp, index of refraction. I kind of can, elevator pitch what this is if I'm really in that scenario. But I don't know every single word or every single equation in this section. I just feel like I don't really want to take a look at it. So I'm going to keep sliding through the chapter until there's a bunch of stuff here, until I hit this. So when I first read through this chapter, Huygens principle was something that I had no idea what it was about. And it's 35.6. I went through it very quickly last read through of the chapter, and it's just itching my brain a little bit. I want to see what this guy Huygens was talking about. So I will start today with this section. But this is just an idea to share with you guys. Feel free to start in any section of the chapter. Whatever interests you most, I think would be the best. Or if you don't really know and you just have you don't know what interests you most and you just have a strong grasp of the starting 1, 2, 3 first sections of the chapter, like I said before, you can start with the last section, start with the end of the chapter and just read backwards. And that also fills in the blanks fairly nicely. It's an interesting technique. Might not work for everybody, but you could try it out if you want. So I'm going to start reading this section here, and I will start with this little pitfall prevention over here. Let's take a look at what this says. Pitfall prevention 35.4. Of what use is Huygens principle? At this point, the importance of Huygens principle may not be evident. Predicting the position of a future wavefront may not seem to be very critical. We will use Huygens principle in later chapters to explain additional wave phenomena for light, however. Okay, Cool. Not the most useful series of words, but you know, cool. Now I'm going to start with the main section. In this section, we develop the laws of reflection and refraction by using a geometric method proposed by Huygens in 1678. Okay, awesome. Huygens' principle is a geometric construction for using knowledge of an earlier wavefront to determine the position of a new wavefront at some instant. In Huygens' construction, all points on a given wavefront are taken as point sources for the production of spherical secondary waves called wavelets that propagate outward through a medium with speeds characteristic of waves in that medium. After some time interval has passed, the new position of the wavefront is the surface tangent to those wavelets. I'll be honest with you, I have no idea what any of that meant, but I read it once. Let's just keep pushing through, and maybe it'll start piecing itself together. First, consider a plane wave moving through free space as shown in figure 35.18a. Whenever I see a figure like this, I just pause the sentence real quick and find the figure just so I have something in my mind. So 35.18 is this here. We can read the bottom title, Huygens construction for A, a plane wave propagating to the right, and B, a spherical wave propagating to the right. So you can see A is right over here. I highlighted it, and it shows you old wavefront, new wavefront, some little red red circles, C delta T in the middle over there. You see some letters A right over here. I can't highlight that. A and A prime, B and B prime, and then part B is the same thing but in a circular looking shape. Okay, so if this doesn't really, make sense to you, it's okay. It's just good to see what the image is. So we'll go back and read that again. First, consider a wave. First, consider a plane wave moving through free space as shown in figure 35.18a. At t equals 0, so time equals 0, the wavefront is indicated by the plane labeled A prime. You see the plane labeled A prime. At the top of that blue line is A, at the bottom is A prime, and that's a whole plane. You can imagine a picture drawn on a 2D piece of paper, and the plane going in and out of the piece of paper like this, and the little blue line labeled A prime is just a cross section of that plane. So in Huygens construction, each point on this wavefront is considered a point source. For clarity, only 3 points on AA are shown, AA prime. And you can see the 3 points here. Each of those points is the center of that red circle that you see kind of on B prime. With these points as sources for the wavelets, we draw circles, each of radius c delta t, where c is the speed of light in vacuum and delta t is some time interval during which the wave propagates. The surface drawn tangent to these wavelets is plane B prime, which is the wavefront at a later time and is parallel to A prime. In a similar manner, figure 35.18b shows Huygens construction for a spherical wave. Very, very interesting. So what we read here was the first 2 paragraphs and the first image of section 35.6, and it kind of fits together what is happening. The next big bulk in Huygens' chapter here is Huygens' principle applied to reflection and refraction. The laws of reflection and refraction were stated earlier in this chapter without proof. Now we derive these laws using Huygens' principle. Cool. And here they actually derive the law of reflection. And a little bit later, they derive the law of refraction, which is this equation here. And that's the end of section 35.6, Huygens' principle. So a little quick read through of this. You don't have to understand everything that's happening in this chapter, but you can see how this is a much deeper read through than the 7-minute run through. 7 minutes, I kind of just read the first sentence of this. I read the chapter, and maybe I saw an image or two, and that's it. But now I understand that this gentleman, Mr. Huygens, has found a way to talk about waves moving through space, and he brings in this concept of the wavelet, which is kind of like a tiny point source creating spherical waves, and a combination of these at a later time and a further location from the source creates a combination which could be considered like the entire wave. This is not exactly the ray approximation. It is more of a wave. They call it geometric construction using the knowledge of earlier wavefronts to determine position of a new wavefront at some instant. So you can see how it's kind of a new thing, but it interlocks with the chapters we read before. That's why I recommended starting with a section later on in the chapter that you're not really comfortable with, because even if you're uncomfortable with the first couple sections, if you're bored reading through those, very little information is going to get into your head. So you can jump into a section in the chapter that interests you. So I started with 35.6, and you can see how it actually builds on to the previous sections. Here we actually derive the two laws that we learned about earlier in the chapter. The reflection law, which is theta 1 is equal to theta 1 prime, and the refraction law, which is this kind of a ratio here. They don't write it in a ratio here, they write it as like one line. N1 sine theta 1 equals N2 sine theta 2, which is Snell's law, or the law of refraction. Okay, I'm going to leave it at that. We're going to do more problems later, and we're going to look at these derivations a bit more closely. I just want to do a little read through with you guys here today to show you that it's okay to read through this a little bit. It's okay not to understand everything at the first go, but it is good to spend a bit of time reading it. So now that we're in the final sections of the chapter, I'm going to keep reading, just get a bit of theory, because if you remember my 7-minute read through of the chapter 35.7 dispersion, I spent literally 0 time on it. We're going to read the first couple of paragraphs, but first let's just see how big the section is. So we have about 2 to 3 paragraphs on this page, 2 images. We have another image here and maybe a few more paragraphs, looks like 3 paragraphs. Another pitfall prevention. We have a quick quiz, and that is the end of the section. So very short, it's like half a page here. Let's start reading through it. An important property of the index of refraction, n. So remember previously we kind of skipped through this. If you feel uncomfortable with this, you can go back and read what the index of refraction is. But if you don't feel like doing it and you just want to learn about dispersion, you can keep reading, and later you'll build up on your knowledge of what the index of refraction is. Just keep it in your mind that it's something that you might not fully know right now. Take a note, and then later when you have some time, go back to it and read what is the index of refraction. An important property of the index of refraction, n, is that for a given material, the index varies with the wavelength of light passing through the material, as figure 35.2 shows. 35.2, so we can take a look at this figure. It's a little bit strange looking, but you can see the x-axis is lambda in units of nanometers. So this is the wavelength of visible light. From 400, where it's around the blue end, 400 nanometer wavelength is around blue light. And then you move on to the 700 nanometer wavelength, which is red light. And all between that is in the entire visible spectrum of light. We haven't really talked about that too much in this chapter. Just take it in as knowledge and try to see what this specific section is talking about. So this figure specifically is showing you n, lowercase n, which is the index of refraction, as a function of wavelength of light for different materials. And here we have 3 different materials: crown glass, acrylic, fused quartz. So they're telling you that the index of refraction lowers as you get higher up in the wavelength of visible light. So blue light entering crown glass will experience about 1.53 index of refraction, which changes its refractive angle. It means it refracts at a different angle than, for example, red light at 650 nanometers, which has an index of refraction at about 1.51. So the index of refraction changes by 0.02 about. But that small change actually has an effect. If we go back to the previous section over here and we take a look at Snell's law, you could see the refractive index is actually over here in this equation. So if the refractive index changes, then theta 1 and theta 2, the angles will also change. Interesting, just a little bit of a thing to keep in mind. Let's keep reading here. This behavior is called dispersion, and they bold it. And it's also the title of the section, so that's important. Because lowercase n is a function of wavelength, Snell's law of refraction indicates that light of different wavelengths is refracted at different angles when incident on a material. That's what I just said before. So when you have a different material and you have different color light passing through it, the angle that it refracts at is different. We haven't really gone through the refraction law too much in this channel, but once we get into it and we do some problems, this dispersion relation is going to be something good to keep in mind. And it also relates to the rainbow. As you can see here, actually, in this prism, you can see a little bit of a rainbow forming. Don't worry, we will get to that. Figure 35.21 shows that the index of refraction generally decreases with increasing wavelength. For example, violet light refracts more than red light does when passing into a material. Now suppose a beam of white light, a combination of all visible wavelengths, is incident on a prism as illustrated in figure 35.22. Clearly the angle of deviation, delta, this is a little Greek letter, lowercase delta, I believe. The angle of deviation delta depends on the wavelength. The rays that emerge spread out in a series of colors known as the visible spectrum. This is also bolded, very interesting. Visible spectrum, maybe you can peep that in Wikipedia later and see what they're talking about here, because it hasn't been introduced earlier in this chapter. These colors in order of decreasing wavelength are red, orange, yellow, green, blue, violet. Newton showed that each color has a particular angle of deviation and that the colors can be recombined to form the original white light. Okay, that's crazy. First of all, these colors in order of decreasing wavelength are red, orange, yellow, green, blue, violet. Roy G. Biv, I think that's how I remember it as a kid. Maybe indigo is in there to make the Biv, B-I-V. But those are the colors of the rainbow. So very cool how you're building up towards the rainbow. So yeah, we will see that. Let's actually just read this very quickly. Figure 35.22. White light enters a glass prism at the upper left. A reflected beam of light comes out of the prism below the incoming beam. The beam moving toward the lower right shows distinct colors. Different colors are refracted at different angles because the index of refraction of the glass depends on wavelength. Violet light deviates the most, red light deviates the least. Okay, the first couple sentences in that kind of confused me, but it pretty much summarized this whole dispersion main section. So let's go here, and as you remember, everything you see here on the page pretty much completes the dispersion section. So let's read through it quickly, but let's take a look at this image here first. Active figure 35.23. Path of sunlight through a spherical raindrop. Light following this path contributes to the visible rainbow. Sign in at blah, 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 to vary point at which, okay. So we have actually a diagram of a water droplet here with sunlight entering and refracting inside the water droplet because the water has a different index of refraction than the outside air. So there is an angle here of refraction. And you can see the red and violet colors refract differently. They have different paths because their wavelength is different, so they refract differently, which is the whole first section we saw there of dispersion. And you can actually see they show you angles 40 degrees and 42 degrees, which is from the incoming sunlight, which angle the final rainbow rays are coming out at. So just a little diagram there, not too important to remember, but pretty interesting to see. The dispersion of light into a spectrum is demonstrated most vividly in nature by the formation of a rainbow. Let's go! We're finally talking about the rainbow, which is often seen by an observer positioned between the sun and a rain shower. To understand how a rainbow is formed, consider active figure 35.23, which we just read. A ray of sunlight, which is white light, very important, passing overhead strikes a drop of water in the atmosphere and is refracted and reflected as follows. It is first refracted at the front surface of the drop with the violet light deviating the most and the red light the least. At the back surface of the drop, the light is reflected and returns to the front surface, where it again undergoes refraction as it moves from water into air. The ray leaves the drop such that the angle between the incident white light and the most intense returning violet ray is 40 degrees. And the angle between the incident white light and the most intense returning red ray is 42 degrees. This small angular difference between the returning rays causes us to see a colored bow. Now suppose an observer is viewing the rainbow as shown in figure 35.24. Let's peep figure 35.24. It is this one here. The formation of a rainbow seen by an observer standing with the sun behind his back. Okay. Cool. I guess they're showing us kind of the same thing as here, but a larger view. Let's keep reading. If a raindrop high in the sky is being observed, the most intense red light returning from the drop reaches the observer because it is deviated the most. The most intense violet light, however, passes over the observer because it is deviated the least. Hence, the observer sees red light coming from this drop. Similarly, a drop lower in the sky directs the most intense violet light toward the observer and appears violet to the observer. The most intense red light from this drop passes below the observer's eye and is not seen. The most intense light from other colors of the spectrum reaches the observer from raindrops lying between those two extreme positions. Okay, that whole paragraph was a little bit confusing with the below the observer's eye and intense. So I'm just going to keep moving, but I'm going to keep it in my mind that it's a little bit confusing what they're talking about here. And it might be something that I should read up on a bit later. But for now, I just want to get a broad view of what's happening, so I'm going to keep reading. The opening photograph of this chapter shows a double rainbow. The secondary rainbow is fainter than the primary rainbow, and the colors are reversed. The secondary rainbow rises from light that makes two reflections from the interior surface before exiting the raindrop. In the laboratory, rainbows have been observed in which light makes more than 30 reflections before exiting the water drop. Because each reflection involves some loss of light due to refraction out of the water drop, the intensity of these higher order rainbows is small compared with that of the primary rainbow. And that completes the section. So they actually mentioned the opening photograph shows a double rainbow. I kind of like taking a look at this just to see what they're talking about. So let's go to the beginning of this chapter and see the opening. Not that. Bruh. Okay, it may have been this. Image not available due to copyright restrictions. Very beautiful. Here we see the double rainbow. The lower rainbow is a bit brighter and the upper rainbow is more dim. And it does look like the colors are reversed. You could see the lower rainbow starts with kind of a purple, then it goes to red, orange, yellow, green, blue. The upper rainbow starts with the blue, and then it goes green, it's kind of fuzzy, and then it's a bit yellow, orange, red, and then it ends with kind of a purple-ish looking color. Okay, pretty interesting. So let's go back, and we're at the final section here before we get into the summary. And the final section is total internal reflection. So at this stage, my brain is getting a little bit fried. You know, I read some stuff, and like I don't know if I'm feeling reading this too much, but since I'm already here, you know, I've kind of gone through the textbook a bit. I'm just gonna finish off with this section so that I have like a nice broad view of every single section, and at least I've read each in detail, right? I know these equations here might be kind of like a little spooky, but let's just keep reading it as we've read the previous two sections, and then we'll complete and take like a big view of the chapter and see how we feel. So 35.8, total internal reflection, an interesting effect called total internal reflection, again bolded, and the title of the section, so pretty important. Maybe you can write this down and be like, oh, okay, total internal reflection, this is an important thing. Like, what is it? Can I summarize it in a couple sentences? Total internal reflection can occur when light is directed from a medium having an index of refraction toward one having a lower index of refraction. All right, consider active figure 35.25a, page 994. 35.25a. Looks like a bunch of stuff is happening here, but it reminds me of the previous two sections where we saw, you know, a slab of glass or something, and we see a light ray refracting and reflecting. Here it looks like there's multiple light rays, and they're doing both refraction and reflection. So a little bit confusing. It's making me feel a bit uncomfortable, so I'm just going to keep reading. I don't really want to look at that image anymore. for now. I'll take a look at it later. But consider the active figure. All right, I've considered it, in which a light ray travels in medium 1 and meets the boundary between medium 1 and medium 2, where N1 is greater than N2. Okay, let me actually check where N1 is greater. So N1 is that like blue medium, maybe it's like a chunk of glass or something, and N2 is the white on the upper side. And they're saying that N1 is greater than N2. Okay, cool. In the figure, labels 1 through 5 indicate various possible directions of the ray consistent with the wave under refraction model. The refracted rays are bent away from the normal because N1 is greater than N2. At some particular angle of incidence, theta C, called the critical angle, again in bold, and you can kind of note that in your mind. Theta subscript C is the critical angle. Theta is an angle and C stands for critical. The refracted light ray moves parallel to the boundary so that theta 2 equals 90 degrees. Active figure 35.25b. I don't know what that means, but let's take a look at it here. So this image here, you could see the light ray is coming in and it hits the boundary of the two mediums, N1 and N2, and the light ray reflects back into it. It looks just like reflection, and there is no refracted light ray. There's no light ray that's going into the white section denoted by N2. Okay. For angles of incidence greater than theta C, the critical angle, the ray is entirely reflected at the boundary as shown by ray 5 in active figure 35.25a. Okay. We can use Snell's law of refraction to find the critical angle when theta 1 equals, okay, some equations. I'm going to save that for another day. There's nothing wrong with equations, but I just kind of want to finish this section here. So I have this section here, 3 paragraphs-ish. Quick quiz, a couple images. Here's an example. And then there's another section on optical fibers, which is very short, half a page, and then the summary. So let's bulldoze through this. We're going to just read the theory, like a little read through, and stay away from the problems and stuff, because for today, I don't really feel like doing that. So this equation can be used only when N1 is greater than N2. That is, total internal reflection occurs only when light is directed from a medium of a given index of refraction toward a medium of lower index of refraction. And that is bolded, so it's pretty important. That means total internal reflection only happens in a specific scenario. And it would be useful for us to kind of remember what that scenario is. But for now, don't stress about it. It's good just like knowing like where you're at. And you don't need to remember everything the first time you read it. If N1 were less than N2, equation 35.10 would give sine theta C is greater than 1. Equation 35.10 is this one, sine theta critical equals N2. Kind of looks like Snell's law. Again, we didn't really go over Snell's law too much, but we'll take a look at that once we're doing some problem solving videos a little bit later. The critical angle for total internal reflection is smaller than... okay, I'll be real with you guys. This stuff here is kind of not really entering my mind. I think it's just repeating the same stuff over and over. So I'm kind of just gonna skip to a new section and go to optical fibers and end off today's little reading session. Another interesting application of total internal reflection is the use of glass or transparent plastic rods to pipe light from one place to another, as indicated in figure 35.28, which is over here on the side. You could see a little blue fiber and the light ray kind of bouncing all over inside of it, kind of like if you throw a marble down like a water slide, or if you just send like a stream of water inside of a pipe. Light is confined to travel within a rod, even around curves, as the result of successive total internal reflections. Such a light pipe is flexible if thin fibers are used rather than thick rods. A flexible light pipe is called an optical fiber in bold, which is also the title of this section. or the title of this subsection. If a bundle of parallel fibers is used to construct an optical transmission line, images can be transferred from one point to another. This technique is used in a sizable industry known as fiber optics. A practical optical fiber fibers, a practical optical fiber consists of a transparent core surrounded by a cladding, a material that has a lower index of refraction than the core. The combination may be surrounded by a plastic jacket to prevent mechanical damage. Figure 35.29 shows a cutaway view of this construction. 35.29 is over there, okay. Because the index of refraction of the cladding is less than that of the core, light traveling in the core experiences total internal reflection if it arrives at the interface between the core and the cladding at an angle of incidence that exceeds the critical angle. In this case, light bounces along the core of the optical fiber, losing very little of its intensity as it travels. Any loss in intensity in an optical fiber is essentially due to reflections from the two ends and absorption by the fiber material. Optical fiber devices are particularly useful for viewing an object at an inaccessible location. For example, physicians often use such devices to examine internal organs of the body or to perform surgery without making large incisions. Optical fiber cables are replacing copper wiring and coaxial cables for telecommunications because the fibers can carry a much greater volume of telephone calls or other forms of communication than electrical wires can. Wow. Okay, that last paragraph was actually very interesting. Personally, I think it's interesting. You know, you might find it boring, but each people have their own interests. So I find it kind of cool that optical fibers are used in medicine and communication. And in one, like medicine, or I guess, let's say surgery, they're using it to kind of see inside the body with like, you know, very small damage. Like you don't have to cut open a whole section to see what's happening inside. You could just like slide in this very thin coaxial, or you can slide in a very thin optical fiber and take a look at what's happening. And in another section, they're replacing old school. It's not old school. When you learn electricity and magnetism, you can see that copper cables and stuff like that are very useful, but it's interesting seeing it used there. Okay, so I think that ends off the video today. You can see here is the summary section, which I went through last time. And again, you can kind of ask yourself, what parts of this are you kind of uncomfortable with? So let's take a look at the beginning of this. So to summarize again, we have the nature of light, measurements of the speed of light, ray approximation in geometric optics, the wave under reflection, the wave under refraction, and what we went over today was Huygens principle, dispersion, and total internal reflection. So a broad view of the book, and you know, I know I'm repeating the sections a lot in this channel, but I think it's very good to remind yourself over and over what you're reading, because then it forms like a nice little organized folder or tree diagram in your head, and you can like go back to it very quickly. Like you can think back, okay, what did I learn in chapter 35? That was the chapter about light and reflection, refraction. It ended off with some stuff about fiber optics and the rainbow. So you can kind of get a very nice overview of everything, and then you can dive deep into, you know, what problems you have to work on to, you know, do well on homework and stuff like that. So I hope this was helpful. We'll talk